Good day, robotics competitors, and thanks for tuning in. My name is Sheldon Marquis, and I'm here today to teach you all about the essential knowledge you'll need to start competing in this year's robotics competition. In this series of videos, I'll be teaching you about the fundamentals of electricity, basics on how to create an effective but clear circuit diagram, and things to consider for the provincial/national competition. For this video, we will be learning the fundamentals of electricity. Now, let's start with the basics. First, I'm sure you've heard the saying that opposites attract. This can actually apply to electricity as well. Let me explain. As we can see here, as I'm sure you've already learned in school, a simplified model of an atom consists of a positively charged center, or nucleus, and some negatively charged electrons orbiting around the nucleus. In a very simplified but fundamental way, the electrons are attracted to the positive center. If we were to put a positively charged particle close to a negatively charged particle, just like I was saying before, opposites attract, they would actually try to move towards each other. Let's say if we had a positive charge and another positive charge. Going by that same rule, since they're the same kind of charge, they would actually repel each other. Same thing goes for negative and negative. They would also repel from each other. So that's pretty straightforward. In most materials, electrons just sit in place and don't move around too much, like this piece of a paper towel that I've been using to wipe the board. But now, in terms of metals, like wires or anything like that, or copper, electrons actually move around and are able to be inside a sort of kind of electron sea, and they actually can move around and conduct electricity, and that's why we call them conductors. Now, let's go here, and we're going to draw some atoms with some electrons, as such. So, we can imagine this being a wire. Let's say the electrons are orbiting these positive nuclei. What I'm trying to describe is basically that this electron is free to move around between atoms. There's no restrictions on them, whereas a piece of a paper towel, they don't conduct electricity as much because the electrons don't have quite the ability to actually move across the material, whereas metals, they do. So moving on to the next one. The electrons are actually free to move around within the material while the nucleus still preserves copper solid structure. This type of material is what we call a resistor, since it has the ability to conduct electricity. Now, I'm going to give you an example of what we are looking for, since we now have the basics down. So, let's imagine we have a wire made of a conductive material that is 1 atom in thickness. So here's your atom right here with the electron orbiting around, same with this one. Then another electron. Since these electrons are free to move around as discussed previously, if I were to push one electron, let's say this one, into this guy's orbit, going off of our knowledge before, since the same kind of charges repel each other, if this guy was to go into the orbit, this would push this electron over to the next orbit, and so on and so forth. And that basically gives us electrical current. And that's basically how we push electrons through a copper wire. One electron jumps to the other and to the other. If it was 1 atom thick. If it was a lot thicker, obviously, electrons would just flow. And this basically causes a chain reaction down the line. Now, if I were to keep pushing electrons through the line, a kind of flow would start. This is basically what electric current is. When electrons are flowing through a conductor, you could say that there is an electric current in that conductor. But how do we measure that flow? So now we have, let's say, a wire with a bunch of electrons kind of flowing through. How are we going to measure that flow? In the electrical industry, the flow is basically a certain amount of electrons that pass through a certain point per second. Kind of like how you measure water flow as liters per second. So if we were pointing at this direction, we wanted to measure how many electrons are passing by per second, you would just have kind of a counter. The way that we actually measure this is called an ampere, or amps as we shorten. So that would be amps. And the fundamental measure of this is 1 amp is equal to 6.24 times 10 to the power of 18 electrons flowing through a certain amount or a certain point per second. Now this, you don't need to remember the exact amount of electrons there are in a measurement of 1 amp. You just need to know that electrical current or flow is defined as a certain amount of electrons moving through a certain point per second. Therefore, if you were to double the amperage through a circuit, you'd subsequently double the amount of electrons that flow through a certain point per second. But now, what we want to know about is what exactly is pushing those electrons, because like what I was showing before, I wasn't physically pushing electrons into the wire. We actually need to learn about something called voltage. So I'm going to draw a battery here. So these are pretty fundamental symbols that I'll be showing you in a little bit in our next video. But basically, here's a battery. And then we have the wire coming up, coming down, and then say we have a little light here. Kind of like that. And over here. So, one of the fundamental things I want to talk about is voltage. So, voltage behaves like a pushing force, forcing electrons to start moving around the circuit, which creates an electrical current. Let's imagine that this battery over here is 12 volts. So that means it has the potential to push electrons along the circuit, down into the light, and then back into the battery. The bigger the pushing force, i.e. the bigger the voltage, the more current can flow through a circuit. And just be aware that this is a very simple but helpful simplification. What's actually happening is there's a chemical reaction within the battery that causes a voltage to occur between both sides of the battery. One side of the battery is the negative side, and the other is the positive side. As we've learned before, like charges repel. Therefore, since electrons are negatively charged, they will be repelled from the negative side of the battery and start flowing to the positive side of the battery over here. The larger the voltage, the more electrons will flow through a certain point per second, i.e. the larger the voltage, the more current's going to flow through the circuit. A side note, I'm sure traditionally you've heard that electricity flows out of the positive side of a battery and flows into the negative side. This is known as conventional current and is the opposite of what we have learned today. So this is what conventional current looks like. It's called conventional current because this was what scientists had assumed was the way electricity flowed when it was first being studied, but this was of course an educated 50-50 guess that turned out to be wrong. However, many of our fundamental equations use this direction of current as a basis, so instead of going back and changing the equations, scientists just decided to call it conventional current and not change anything else. So moving forward, let's just pretend that electrons flow out of the positive side of the battery and flow into the negative side of the battery. Just because. Now, the next fundamental piece of a circuit we want to learn about is resistance. As we discussed previously, we thought of electrical current as a certain amount of electrons moving through a certain point per second, like liters per second through a tap. So if I were to draw it like that, I'd have a bunch of electrons passing through a certain point, like through a tap. Now, what if I were to draw a wire that had atoms inside of them, but then they're fewer and farther in between each other? Or maybe even one of them, or maybe a lot of the atoms don't even have enough electrons to allow for proper flow through it. What exactly happens? What we basically have now is a material that resists electrical current. So imagine if I'm trying to push an electron into this atom, but then it can't really push it into this one. What happens? Well, basically the electron will go over here, and then will be repelled back, and then it'll actually cause some heat to come off. And that's what we call electrical resistance. Basically what that means is the material resists flow of electricity. And how we measure that is in something called an ohm, just spelled OHM, which is equal to the omega symbol. I'll draw you a little better one, which looks like this. And that's how we measure resistance in an electrical circuit. Now, let's say we have an electrical conductor. This has very, very low resistance because it's able to conduct electricity very well. But if we had something like a resistor, they have higher resistance and therefore they resist electrical current a lot more than a conductor. When something resists flow, it heats up since it is resisting the movement of electrons. As an example, a heater that you plug into the wall has a high measure of resistance, and therefore it heats up when introduced to an electrical flow. Now let's draw a circuit to give more of an example of what's going on. So we are going to have a battery here. Plugged into a resistor, and that's in a resistor's symbol, as well as a light. Let's just draw it like that. One of the points of having a resistor in a circuit is to restrict the amount of flow through a circuit, which then gives us control over how much current flows through a circuit. So if we're looking over here, we have a current flowing through, and if we added in a resistor here, it's actually slowing down that flow so that and then it puts that energy out as heat, right? And so when we put that resistor in there, it actually limits the amount of electricity that gets to the light, and therefore it could dim it, it could brighten it, it depends on our resistance, right? With this, we have now learned the 3 fundamental variables in electricity, and can now start doing some math with Ohm's law, because we all love math. So, what we learned first is V is equal to voltage, I is equal to current in amperage, or amps. Let's just write amps. And then resistance is equal to R. It's measured in ohms, which is the ohm symbol there. So now we could actually combine these into a single equation called Ohm's law. Basically what Ohm's law is voltage is equal to current, which is denoted by I, times resistance, which is denoted by R. And I'll just make that a little more clear. Where V equals voltage, I equals current, R is equal to resistance. Using this formula, we can make decisions as to how much of a resistance we need to add into a circuit to limit the amount of current flowing into a device. So, what I mean by that is, say we have a 9-volt battery, like those typical ones that you have 2 prongs on them, just over here using the same symbol as I've used previously. And now let's say we have an LED over here, and the manufacturer tells us, let's just draw it as a light again. Let's just call it a LED, but you know, it looks like a light. Let's say the manufacturer tells us that you could only put in, let's say, 10 milliamps of current through it, and it only runs at 3 volts. So across here, it could only be 3 volts. So first thing we gotta know is that 9 volts over on this side really means from here down to up here, it's 9 volts. And we want it to be 3 volts here. So 9 minus 3 is 6 volts, which will be across this resistor. And so now using our formula V is equal to IR, and knowing that through this circuit we want to have 10 milliamps, which is equal to 0.01, we want to be able to find the resistance required to limit this to those parameters. So basically all you have to do is divide I over, so V over I is equal to R, which is equal to 6 volts from up here, divided by 10 milliamps, which is 0.01 of an amp. And if we take our trusty little calculator that I brought out here, we could do 6 volts divided by 0.01. We get 600 ohms. And so now we could go out to the store and pick up a 600 ohm resistor. This will be 600 ohms. And basically what we get is a safe circuit, because now we could power this LED properly without running the risk of blowing it up. Because the manufacturer told us it could only run at 10 milliamps at 3 volts, it's safe now. Now, speaking about power, I know you've probably heard before the term wattage. I think I'm going to go into that into more detail here. The next thing we want to learn about is electrical power. Electrical power is defined as the rate in which energy gets supplied or is used up. Therefore, in electricity, we measure this in watts, which is measured as 1 joule of energy per second. So basically, watts are the transfer of energy from one device over to another. So this would be kind of like a battery going into a light. Just like at home, we could say that you're running a 30-watt lamp. Basically, that's how much energy is actually being outputted, which gets converted into light. I guess that'll be a light symbol, and then heat as well, because they heat up, obviously. So the power is the energy transfer from the battery. Now, in order to calculate this, there's actually a pretty simple formula. We remember that V is equal to IR. But now we also have the formula power is equal to volts times current. And that's also equal to the current squared times the resistance. Because if you do some fancy algebra, you could actually put this formula into that one to get P is equal to I squared R. So basically, up here, I'll just give you P is equal to I squared R, or P is equal to volts times amps. So let's say we were using that same example as we had previously, where there was a 600 ohm resistor, which had 6 volts across it, and then we also had a light, an LED light that needed to have 10 milliamps, which is flowing through the circuit, and it needs to run at 3 volts. What sort of wattage are we looking at here? So basically all we have to do is power of the light is equal to the volts, which is 3 volts, times the current flowing through it, which is 0.01, which is equal to, I'm sure this is easy enough for you to calculate, but I'll just show you just in case. It's equal to 0.03 of a watt. Now, if we wanted to do the same calculation for the resistor, we could also do the other formula, which is basically power is equal to I squared R, which is basically 10 milliamps squared times the resistance, which is 600 ohms, which is equal to 0.01 squared times 600, which is equal to 0.06 watts. So basically, if the manufacturer was telling us that whoever made the resistor said that it has a certain power rating, most resistors, like these ones over here, they have a quarter-watt resistance, quarter-watt power rating. So 0.06 watts across this resistor is perfectly fine. Now let's say if the current flowing through there was 2 amps, what sort of power would we get? Basically, we would just do 2 amps squared times 600, which is basically 2 squared times 600, which is equal to 2400 watts. Now let's say a manufacturer said they could only handle a quarter of a watt, and you push through 2400 watts into that resistor, it's going to blow up. And that's something that we're kind of trying to avoid. The last thing I wanted to talk to you about is safety, because we all love safety. So, for the most part, when we design our robots, we assume everything goes ideally and no accidents occur. But now let's say I'm going to design a robot here with a battery, and then it's powering a receiver, and then it's powering, I don't know, some motors. Let's just put the motor symbol there. This is not what the symbol usually should look like, but let's just say that happens. And we have a certain current flowing through. Let's say 3 amps or something like that. And that's after these guys are plugged in. So these are resistive loads that are giving off heat and using that energy up and heat. So it's resisting the current and therefore limiting this current. Now let's say you shorted something in the robot, and now one of these motors actually becomes shorted. So now there's not as much resistance. So now the current actually gets bigger. It could even go up to, let's just say as an example, 7 amps. And 7 amps passing through this receiver or through the motor can maybe even cause a fire. And we really don't want to do that in the competition. So what do we do to limit that? Well, there's basically 2 things you could do. First thing, you could install what's called a disconnect switch. So now let's say we're just driving along and we all of a sudden see that one of the motors is shorted and we start seeing sparks. All I'd have to do is go over to the disconnect switch and flip it. And now all of a sudden the current is gone because it can't make it across this air gap. And now the current has stopped and the fire no longer happens. These disconnect switches are very important, and it's in the scope as well too, because they're a safety device and they need to be as visible as possible. That's why we tell you in the scope, make sure your disconnect switch or any breakers or anything like that are visible so that the judges or anyone else can go over to the robot if it's going crazy and just flip a switch and turn it off. That's one way to do it. Another way to do it is what we can do is actually use something called a fuse. So this is a fuse symbol here. Basically what the fuse does is it's rated to a certain amount of current. So it's basically a flimsy piece of metal. And let's say it's running 2 amps through here right now. And so it's lower than the current rating of the fuse. So basically nothing's going to happen. As soon as it gets to like 7 amps, the current is a lot higher than the rating of the fuse, and basically there's a piece of metal that burns out if it goes higher than a certain amount of current, and it burns out so much in such a way that it just disconnects, and all of a sudden, just like a disconnect switch, it's just an air gap. And now any current flowing through there is non-existent. Now, in the scope, it depends on what you want to use. You could either use a disconnect switch or you could use fuses. In terms of safety, it's best to use a disconnect switches for when people are nearby to the robot, and fuses when the robot's running crazy and no one can really get over to it. Because fuses automatically cut off power for you. You don't have to worry about flipping a switch. Now we have everything we need to draw a great circuit diagram. Like I was showing in chunks before, but I'll try and show you again. We have what's called a battery. This is one symbol. Next we have fuses with a certain rating, let's say 5 for now. A resistor. And we could also even make up our own. We could say this is like a receiver. But in the next video, I'm actually going to go over what these symbols can actually help with. Because if you have these symbols set up in such a way, you could actually show to the judges if your robot is safe or not. And that's one of the requirements of the scope, is to actually have a legible kind of circuit diagram, which I'll be showing you in the next video. So yeah, thanks for tuning in.